when we use the equation, so start with the general energy balance. Okay, Q is to the system, put the Q and W work okay, into the system. So initially we have E in minus E out equals to delta E, or Q minus work equals to delta E. Okay, and the delta E equals to delta U plus delta KE plus delta PE. But we know that delta KE and delta PE is equal to 0 because this is what do you call it? It's not in motion. Okay, it's not in motion. Okay, so we have Q minus work equals to delta U. Okay, but work is actually, okay, work is actually, we have two types of work involved in here, which is work of shaft and work of boundary. The boundary is for the piston, the lid of the piston. Okay, so we have delta U is equal to U2 minus U1. So Q minus work other minus work boundary equals to P naught, okay, in bracket V2 minus V1, because this is which case is it? Okay, isothermal. Is it isothermal? Oh no, of constant pressure expansion. Okay, constant pressure, but we have changes of volume, right? So we use work boundary equals to this equation, okay, equals to delta U U2 minus U1. So please create this equation first. Identify your equation first, starting from general energy balance, derive to make until the things that you have, the things you have for based on the condition of your problem statement. Okay, so when you have finished until here, okay, this is just rearrangement of the equation, so you can just put the value inside to solve this problem. Okay, so when we rearrange, we have this equation, and you know that U plus PV is actually equals to enthalpy. Remember? Okay, so U plus PV equals to enthalpy, so actually you have H2 minus H1 at here. Therefore, Q minus work other means your work shaft just now, equals to H2 minus H1. Okay, okay, this is just to show for constant pressure expansion or compression process, work of boundary equals to delta H at here, H2 minus H1. Okay, okay, U plus PV, right? Okay, U plus PV, delta U, work of boundary equals to delta H, H2 minus H1 minus delta U, U2 minus U1. Okay, just to show the relationship. Okay, just to show the relationship. So H2 minus H1 equals to Q minus work. Okay, an example of constant pressure process, we have work in actually your work shaft in just now. Okay, okay, so work in minus Q out minus work of boundary equals to delta U. So how do you arrange this? Okay, remember Q is actually Q in minus Q out, right? Okay, Q equals to work in minus Q equals to Q in minus Q out. Work, okay, work you have to work in minus work out. Okay, or work out minus work in. You need to rearrange this equation. Okay, work out minus work in, but we don't have work out. Okay, but we have work in. So when we rearrange the equation, please recognize your negative and negative positive symbol values. You will get this. Work in minus Q out equals to delta H, and you know that delta H equals to MH2 minus H1. Okay. Okay, so this is your equation that you need to solve. You have the value of work in, you have the value of Q out, okay, and you can find this H2 and H1. Okay, so based on this diagram, PV, and okay, you have V1, you have V2. How do you know this? How do you know that location number 1 is at here? Okay, this is contains, rigid tank contains a hard fluid. Okay, a hard fluid. Okay. Okay, so determine the final internal energy of the fluid. Okay, determine the internal energy of the fluid. Okay, so how do we know about this? Okay, this is saturated vapor. Okay, this is example of saturated vapor. Okay, I'm sorry, this is a different example. Okay, you have been supplied by 0.2 ampere, 120 volt. Okay, you can find the work at here. Okay, mass 25 gram, P1 equals to P2. This is constant pressure process. Q out is 3.7. Okay, I'm so sorry. This is the example for this one. So saturated vapor initially. So this is the location. Okay, so when you you supplied the work and the Q, you have Q out at here. Okay, this is initial. This is final. Okay, the pressure is constant, but you have changes of volume. Okay. Okay, you can solve this problem using the equation. Can you try this first? Okay.